And Mrs. Howard's chemistry class, we're still working on Unit 5, the periodic table and electrons, and we're still looking at the same teaks we were before. We're focused on the periodic table, Roman numeral number 2. Let's see, we've got the same teaks. If I can get through these. Oh, I just got a little bit carried away with the clicking. Alright, we're ready for capital letter B, the periodic table. Periodic table is an arrangement of elements in order by atomic number so that the elements with similar properties fall into the same column or group. Now, those properties are going to show up periodically. They have regular repeating patterns that show up. That's just kind of handy. So it's an arrangement of elements in order of atomic number, and it just nicely falls in line so that they also line up by property. So all of the elements in group 1, all the way down the line, have really similar properties. All of the elements in group 2, right down the line here, they have really similar properties. Letter C, the structure. You can split it into 3 major types of elements. You have metals, which are, they make up the main bulk of the elements there. Though, when you look at the periodic table, if you look at the zigzag line, everything on the left of that is going to be a metal. If you forget, for some strange reason, which side the metals are on, find gold, find tin, find aluminum, find iron. You know those are metals, so find one of those, and you know that, hey, you're on the side of the metals there. Metals are ductile. They can be pulled into a thin wire. They're malleable. They can be hammered into flat sheets. They're lustrous. That means shiny. They're good conductors of heat and electricity, and they're on the left side of the table. Non-metals are on the right side of the table, and they pretty much have opposite properties to that of metals. Now, non-metals, they're not going to be ductile or malleable, or you can't hammer them into sheets. And you know this because, you know, an example of that would be oxygen, which is a gas at room temperature. That's not a metal at all. There's only one non-metal that's on the wrong side of the table, and that's hydrogen. It's just on the wrong side over there. Letter C, the third type would be the metalloids. And these are ones that are kind of iffy. They have some characteristics of metals. They have some characteristics of non-metals. And there are 6 of them: boron, silicon, arsenic, germanium, antimony, and tellurium. Now, you have several periods that you're required to know. You have several, when we talk about the periods, those are the ones that don't necessarily have names. They're actually numbered. So down the left-hand side of the chart, there's 1, 2, 3, 4, 5, 6, and 7. So these are the horizontal rows, and their elements that are arranged just right across by atomic number. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on. The elements in the same period have the same highest occupied energy level or orbit. So if it's in period 3, then the outermost orbit is the third orbit. So you have the first orbit, second orbit, and third orbit. So the valence electrons, the max amount up there, is the third orbit. If they're in period 2, then they only have 1 or 2 orbits. If they're in period 7, they've got 7 orbits out. Oh, look at the pretty pictures. All right. The groups are the ones that you're going to be required to know some of those. And the groups are the vertical columns of elements, and they all have similar characteristics if they're in the same group. The first one that we're going to talk about are the noble gases. Way over on the right-hand side, group 18, these are the ones that are just kind of there, and they sit there and they look at you like, what? They're the ones that don't react. You can try and burn them, you can set them on fire, you can throw acid on them, they're just not going to react. You know, in some labs, high-end labs, they can force a few reactions on them, but for all intents and purposes, they just don't react at all. So, helium, neon, argon, krypton, all those are noble gases. Group 18. Oh, look, it says next slide. That means we'll come back, just skip the number 1 there, and we'll come back and hit it on the next slide, so I spread it out a little bit for you. They're very, very unreactive, which is what I just said, and they're helium through radon. So let's go see what number 1 is supposed to say. Number 1, the outer energy level electrons are called valence electrons. I think you've written that down before. I bet that's kind of important. So the outer energy level, the outer orbit electrons are called valence electrons. These are the ones that are involved in chemical reactions. Oh my gosh, put a big arrow on that one again. The valence electrons are the ones that are involved in chemical reactions. These valence electrons, once we have them here and we start learning about them, they're never going away. We always deal with valence electrons. Noble gases have 8 valence electrons. That's the magic number. Once they get that 8 valence electrons, they are naturally stable. The only exception to that with noble gases is helium, and it's stable with 2 because it's so tiny. Its first orbit can only hold 2 electrons, and that's it. It's full. It's finished. It's not going to react anymore. So it's stable with 2. All the rest of them, their outer orbit has 8 electrons. And they're stable. So that 8 is kind of a magic number. Nobody invented it. It's just that they found out that, oh, hey, when they get 8 in there in that outer orbit, that kind of brings it in that says, hey, it's stable now. All right, next one you need to know are the lanthanides and actinides. That piece that's taken out down at the bottom, these are the rare earth metals, lanthanides and actinides. They're the ones that also have very, very similar properties. And the main reason that they're put down separately at the bottom is just that it makes the periodic table more manageable. It's shorter, it fits on a nice little single page there. So it's a space-saving purpose, really. Oh, look at that. Look at that. Plutonium and uranium are in the lanthanides and the actinides. And there's astatine out there. All right, letter C, the halogens, that's group 17. They have 7 valence electrons. They are the most reactive nonmetals. They're so close to having that magic number of 8, it's so easy for them to steal an electron from somebody. So these are nonmetals, and they react with the metals way over on the far side in group like 1 or 2, and they form salts. So a metal, a nonmetal over here and a metal over here can bond to form a salt. So here you go. You have group 17, and it's got a Roman numeral 7. We'll talk about that later. But you see fluorine, chlorine, bromine, iodine, all those things there. He stole my 1 electron, and now I'm just a naked little nucleus. Hydrogen has 1 proton and 1 electron. That's pretty dead. So if somebody steals this electron, it's pitiful. Again, if you want to pause and read this, it's kind of cool to look at the stuff here. Next one, letter D, are the alkali metals, group 1. So we went on the far side, group 18 and 17, down to the bottom, and now we're going back up over to the left-hand side. Group 1, the alkali metals. They have 1 valence electron, and if they can get rid of that 1, then the next orbit down has the magic number 8. Now, there are a couple of those elements that are so tiny that their next orbit down has only 2 and they're stable there. But the vast majority of them, if they have 1 valence electron out here, the next orbit in has 8. And once they get down to that 8 valence electrons, they're stable. These are kind of silvery, and I'll show you some of this. We'll put some of this sodium in water when we get in class. They're silvery. They're really soft. You can cut them with a plastic knife. They're very, very, very reactive. So reactive that they'll react with the moisture in the air. So the sodium metal that I have is in a glass jar, but it's embedded or it's got oil poured all over it to keep it from reacting with any moisture in the air. So it reacts really strongly with water and air, so it has to be stored in kerosene or oil. I think mine's stored in olive oil. They're not found pure in nature. These guys are so reactive. You're not going to find just a chunk of pure sodium laying on the ground. It's not going to happen like that. So sodium, francium, all those guys, they're not going to be like that. All right, and here we have another piece of the funny periodic table. If I could find this one, I would get a big poster for you guys just so you can see it and enjoy it. So look, there's fluorine, and he's stealing 1 electron from lithium. And when you say they steal it, that means now fluorine is actually going to be in a chemical bond with lithium, so you have lithium fluoride. Next group is group 2, the alkaline earth metals. The alkaline earth metals have 2 valence electrons. They're still metals. They're a little bit harder, a little bit denser, a little bit stronger than the group 1 metals. They're less reactive, but they're still so reactive that you can't find them pure in nature. You're not going to go down and dig in a mine and find beryllium in the pure form. So, again, you're not going to find them in the pure form in nature because they're just too reactive for that. And then you have the big group, the big chunk in the middle that's in the lower section called the transition metals, groups 3 through 12. These are all really strong metals. Copper, platinum, tin, aluminum. You always think, when you think metals, this is where you're looking. That's where iron is. These are the ones that when you think metal, these are what you think of. They're a lot less reactive than groups 1 and 2, but you can still find them pure in nature. In most cases, they can be bonded, so you can find some pure gold, things like that, but in many cases you're going to find silver oxide. You can find veins of silver that are still there, but you'll also find it with, if you have pure silver out, it's going to have a layer on the outside where it's silver bonded to oxygen. That kind of forms a protective layer. So you can find these in their pure state. Oh, that's finished for this one.